Hi friends, welcome to Classical Mechanics classroom. For a change, I am using this blackboard, okay, instead of our usual green board, okay. So, what I am discussing today is rigid body dynamics. So, here, what is mean by dynamics? You know, dynamics is about motion of a body. So, what is the motion of a body? I classify it into three. One is translational motion, rotational motion, and rolling motion. Rolling means it is a combination of translation plus rotation. So I am classifying the motion of a body into three types. Now you are already familiar with the equation of motion in the case of a body in translation motion. Okay, what are those? First one is V equal to U plus AT, and second one, it is S equal to UT plus half AT square, and third one, V square equal to U plus 2AS. Okay, so what is the equivalent equations in rotation? So in rotation, the velocity will be angular velocity and the acceleration will be angular acceleration. So we can write a similar equation of motion for rotation. What are those? First one is WF equal to WI plus alpha t. WF is final angular velocity and this is initial angular velocity, and alpha is the angular acceleration. And second one is S. S is, here it is theta. Theta is equal to omega I t plus half alpha t square. And third one is omega f square equal to omega I plus 2 alpha theta. These are the equation of motion of a body in rotation. And now, what is the second term? That is rigid body. What is its meaning? So, what is a rigid body? The definition of a rigid body is like this: a system of particles in which distance between any two particles is fixed. So that means the shape of a rigid body never changes. What is an example? Example, your iPhone or your bangles. Okay, all these are rigid bodies because if it is in motion, it doesn't change its shape, right? So in a very mathematical way, we can represent in equation form. So I am considering a case of a rigid body. This is a rigid body, and here this is one particle in a rigid body. So it is a system of particles, and this is one particle. I call it as ith particle, and there is another particle, and I call it as jth particle. So from a reference point, I can draw a r vector, that is ri vector, and this is rj vector. So magnitude of ri vector minus rj vector should be equal to a constant value Cij is constant. Okay, this is the mathematical condition for a rigid body. And you already learned that for a particle system, that is n particle system, the degrees of freedom is equal to 3n minus nc2, right? And you know, for a rigid body, this degrees of freedom is equal to 6. And you must remember that this degrees of freedom of a rigid body is 6 only in the case of 3D space. Okay. I think you are remembering we are already discussed a problem, a CSIR problem. In that problem, they asked to find out degrees of freedom of a rigid body in D space, D-dimensional space, right? And I think you are remembering that problem. So you do one thing, you go back to the older lecture note and find out this degrees of freedom of a rigid body in 1D space, 2D space, 3D space, 4D space, etc. Okay, so please refer back those lectures and write it down here. So here we are discussing rigid body dynamics, that is rigid body in motion. And you know all the equation and everything about rigid body in translation motion. So translation motion you know. So I am discussing about rigid body in rotation motion. Now we are going to discuss about moment of inertia. So here, what is inertia? I think you already know. Inertia is a tendency of a body to continue its state of rest or uniform motion. Okay, this uniform is an important term. Okay, motion, that is, if there is a body and if it is in a rest, then it has a tendency to continue its state of rest. And if there is a body and it is in motion with certain velocity, so it's in a translation motion, then it continue its state of uniform motion. And this is a uniform motion also. So this tendency of a body is called the inertia. So we can quantify this tendency. Quantify, it's a quality. So we can quantify it in terms of mass. So you may be already know that mass is proportional to inertia. And I told you we call it as a mass when it is in a uniform motion. Suppose it is in rotation motion, then what we call rotational motion. You know rotational motion is a non-uniform motion, right? And we call this mass in rotation as moment of inertia. So you know what is inertia. It is nothing but mass. But what is this moment? I will discuss a little about moment. Okay, suppose I'm multiplying r square with mass. Then it is called the moment of inertia. And it is also called as rotational mass. This is his nickname of moment of inertia is rotational mass. And I am multiplying r with another two quantities. One is f. So this is called moment of force. But you know this guy is nothing but torque. That is rotational force. Now I am multiplying this r with p, momentum. Then I call this guy as moment of momentum. Or he is also called as angular momentum. Or we can call similar to rotational mass, rotational force. So we can call it as rotational momentum. So I think you got the idea about moment. Now we are discussing more about moment of inertia. The notation for moment of inertia is I. Okay, suppose I am taking a rigid body and this is z axis passing through the rigid body, and this rigid body is rotating about z axis. And this, this rigid body consists of a system of particles. So I am considering a particle here. So in a rotation motion, this is a particle, ith particle, and its mass is mi, and this radius is ri. Then moment of inertia I, that is for the ith particle, can be written as equal to mi ri square. But a rigid body consists of large number of particles, right? So total moment of inertia of this rigid body will be equal to summation of mi ri square. So this is for discrete particle system, discrete case. And if it is a continuous body, then it will be equal to I is equal to integral dm r perpendicular square. This is for continuous case, continuous body. And what is this perpendicular? This is perpendicular distance from the axis. So here z is the axis of rotation. So the distance to the ith particle from axis is called this perpendicular distance. And what is the importance of this r perpendicular? Let us consider a case of circular ring or hoop. So this is a circular ring and it is rotating about z axis. The radius of this ring is capital R and mass is m. Now what is its moment of inertia? That is I is equal to integral dm r perpendicular square. So what is the dm element? Okay, so substituting these values, that is I is equal to integral dm r square. So what we get? I is equal to m r square. So here I am considered the reference point as this one. Okay, now I am taking another case. It is similar to the previous case. Here it is rotating about z axis and the mass is capital M, and I am shifting the reference point to here, and from here to mass element the distance is r, and this angle is theta. Now what is the moment of inertia I? That is equal to, from definition, integral dm r perpendicular square. That is equal to I equal to integral dm r perpendicular. So r perpendicular is the perpendicular distance from axis. So that is this one. Okay. And what is the value of this r perpendicular? If this is r and theta, it is r sin theta. Okay, so r perpendicular is equal to r sin theta whole square. So what you get? You get I is equal to m r square sin square theta. So the reference point is important thing. So when you are solving such problems, don't forget to consider the reference point. Now we are going to discuss a little about this mass element dm. Definitely these are very small things, but if you don't know these small things, you definitely make errors when you are solving a problem. So these small things are very important things. Okay. You see, in CSIR problem, suppose in a CSIR problem, actually they never give such kind of diagrams. Okay, if there is a diagram, then you can easily identify the problem, but they give long sentences. So when you are reading these long sentences, maybe you will lose some points, like the specification of reference point, like that. Then you will land on a wrong answer. The interesting thing in a CSIR exam is, suppose while solving a problem, you made a mistake and finally you got an answer. Definitely that answer will be in the options. So what you do? Oh, you think, oh, I solved all the problems and I got the answer. So you think like that. But what is happening actually? Just opposite. You are losing around 6.25 marks because of a small mistakes. Okay, so learn each concept thoroughly and with pakka clarity. Okay, now we are going to discuss about dm, mass element. Here I am discussing a little about mass element dm. So I am taking the mass element in 1 dimension, 2 dimension and 3 dimension. So for a rod, rigid rod, it is a linear and it is 1 dimension. So this is the dm, and if it is a dx, then we can write dm equal to lambda dx, where lambda is the linear density. Okay, rigid body, maybe some disc or something. So this one has 2 dimensions and my dm is this one. And this area element is dA. Then my dm equal to sigma dA, where sigma is the surface density. And if I am considering a cube, if my rigid body is a cube, and if this is a dm, then and this is dv, element, volume element, then I can write dm equal to rho dv. This is volume density. And this lambda may be uniform or non-uniform or non-uniform. And sigma also may be uniform or non-uniform. And rho also may be uniform or non-uniform. What is the difference between this uniform and non-uniform density? Suppose our mass dm is equal to sigma dA, where the sigma is uniform. Okay, then to find out the total mass m, we have to integrate sigma dA, and when doing this integration, we can take this sigma outside the integral, and we have to do integration only over the area element. And if it is non-uniform, then to find out mass m, we cannot take sigma outside the integral because it is dependent. Example problem. Let us consider a circular disk. Here, this problem I will solve in two ways. One, I use Cartesian coordinates, and then I use polar coordinates. So the circular disk is like this. This is a circular disk. It is rotating about its z-axis, and the radius of this disk is r, and total mass of this disk is capital M. Now I am discussing the problem in Cartesian coordinate. Now I am looking at the circular disk from above. From here I am looking down. Okay. So I can see a circular disk like this one. Okay. And what we have to find out is moment of inertia I. And we know the equation for moment of inertia, that is integral dm r perpendicular square. And here we know dm is equal to sigma dA. So here, what is this dA area? So this is the dA area. This is a dA area of a disk. Okay, and from origin this is x, and this thickness is called dx, and this small area is dA, and dA equal to, you know, it is 2 pi x dx, right? And we know sigma is equal to total mass by total area. Total area is pi r square. Okay, so what is dm? Now dm equal to sigma dA, that is sigma is equal to m by pi r square into dA, that is dA is equal to 2 pi x dx. So we got dm. Now we can substitute this dm value here. So we get I is equal to integral m by pi r square to pi x dx into r square. That is r is here x, that is x square. So here we can cancel this pi, and we can take 2m by r square outside the integral. That is equal to 2m by capital R square integral x cube dx. Okay, so what is the limit of dx? It is from 0 to capital R. R is the radius of the disk. So what we get, it is equal to 2m by r square. Integral of x cube is x raised to 4 by 4 and limits are 0 to r. So we get it's equal to 2m by r square into r raised to 4 by 4. So we can cancel 2 and 4 and r raised to 4 and r square. So what we get is m r square by 2. So this is the moment of inertia of a circular disk about an axis passing through its center and perpendicular to its plane. Now we are going to solve using polar coordinates. The same problem in different coordinate system. Polar coordinates. The coordinates are r and theta. Consider this is our disk of radius capital R and total mass m and density sigma is equal to m by pi r square. Now we have to find out the moment of inertia, that is I is equal to integral dm r perpendicular square. So here what is this dm? Dm is sigma dA. Okay, and what is the dA? Area element in polar coordinates. Maybe you know dA is equal to r dr d theta. How this dA is r dr d theta? You see, suppose this is r and this be theta, that is d theta, and this is a element area at a distance r from origin, and this is dr. Okay, so this area dA will be equal to r dr d theta. Okay, so we are substituting all these values, that is I equal to integral dm, that is sigma dA. Sigma we know m by pi r square into dA is r dr d theta into r perpendicular, that is r square. Now what we get? I is equal to, here also you can take the common times, here also you can take the constants outside, that is m by pi r square integral r cube dr integral d theta. Here what is the limit for r? R is from 0 to capital R. And what is the limit for theta? Theta is varying. This is the d theta variation. So theta is varying from 0 to 360 degree. That is 0 to 2 pi. So this limit is 0 to 2 pi. So what we get? M by pi r square. Integral of r cube is r raised to 4 by 4. Limit 0 to r. Integral d theta is theta, and when substituting theta, and substituting 0 to limits 0 to 2 pi. So what we get? M by pi r square r raised to 4 by 4 into 2 pi. This equal to m r square by 2. So we got the same answer, but we solved using different coordinate system. Okay. I am giving a work for you. Okay. You have to find out moment of inertia of a cylinder. This is the cylinder and it's rotating about its axis, z axis. Okay, total mass is capital M and the radius is capital R. Okay, I give you one hint. You can slice this cylinder into discs and you know moment of inertia of a disc. So now solve by yourself. Another work for you. Find the moment of inertia of a rod. The total length of this rod is capital L and the total mass is capital M and it is rotating about this axis. So this is plus L by 2 and this is minus L by 2. So go and find moment of inertia I for this rod. Another example. Example of a hollow sphere. Let this be a hollow sphere. Okay, and this is the axis. And the total mass of this hollow sphere is M. And it is rotating about the axis Z. This is the center point of hollow sphere and let this be a mass element, that is dm, and this is a area element dA, and this is the radius r, and this is the angle theta, and this is perpendicular distance r perpendicular, that is equal to r sin theta, capital R sin theta. And you know, for a hollow sphere, sigma is equal to mass by 4 pi r square. Now we are going to find out the moment of inertia I, that is I is equal to integral dm r perpendicular square. So here dm is equal to sigma dA, and sigma dA is equal to, sigma is m by 4 pi r square into dA. Here this dA is in spherical polar coordinates, that is in terms of r theta phi. We can define area element as, that is dA is equal to r square sin theta d theta d phi. So here this theta can vary from 0 to pi, and this phi can vary from 0 to 2 pi. Okay, so we got dA, so we can rewrite that I is equal to integral dm, that is sigma dA, sigma is equal to m by 4 pi r square into dA, that is equal to r square sin theta d theta d phi. Now r perpendicular square, that is r perpendicular square is r sin theta or square. So here we can take the constants outside, that is I equal to, we can take m by 4 pi. Here r square will cancels, and one more r square will be there, that is mr square. Integral sine cube theta d theta integral d phi. Theta limit is 0 to pi and d phi limits are 0 to 2 pi. Okay, so what we get, mr square by 4 pi into integral of 0 to pi sine cube theta d theta is 4 by 3. I will discuss these concepts, this standard formulas in my mathematical class, mathematical physics class. Okay, so the value of sine cube theta d theta, now you just remember this value of sine cube theta d theta, that is 4 by 3 into integral d phi, that is phi, and after substituting this limit we get 2 pi. So here we can cancel this pi and remaining and 4, and what we get is 2 by 3 mr square. Another work for you. Consider a solid sphere. The mass of the solid sphere is capital M and radius is capital R. Then the density, mass density rho will be is equal to m by 4 by 3 pi r cube. Right, and this is the radius r, and this solid sphere is rotating about this axis. Okay, and this angle is theta, and this is the perpendicular distance or perpendicular, and that is equal to, you know, r sin theta. Now what is moment of inertia? That is I is equal to integral dm r perpendicular square. Here dm is equal to rho dv. And what is dv in spherical polar coordinates? Because in this problem we are using a spherical polar coordinates because this sphere has a spherical symmetry. Okay, so in spherical polar coordinates, dv equal to r square dr sin theta d theta d phi. Maybe you already know this equation, or I will discuss in mathematical class. Okay, here this theta will varies from 0 to pi, and d phi will varies from 0 to 2 pi. Okay, now what you have to do, you substitute all these values in the integral and integrate, so you get the answer. Okay, and write the answer here. Let us discuss one previous net problem. Okay, it is asked in part C. That means this is a 5 marks question. This is a very simple problem. You can easily get this 5 marks. Can you do by yourself? Okay. Okay, I will help you to solve this problem. Okay, so the problem is an annulus of mass m made of a material of uniform density has inner and outer radii a and b respectively. So this inner radii is a and outer radii is b. Okay, its principal moment of inertia along the axis of symmetry perpendicular to the plane of the annulus is. So this is that axis. So we have to find out moment of inertia about this axis. That is the question. So how we solve? We know moment of inertia I is equal to integral dm r perpendicular square. So here what is dm? Here dm is equal to sigma dA. And what is dA? Here suppose this be radius r. I am taking an arbitrary radius. This be radius r. And I am considering an element, area element, this one. Okay, so this is thickness is dr. Okay, so dA will be equal to, this is the dA element. So this dA will be equal to 2 pi r dr. And what is sigma? Sigma is equal to total mass by total area. So that is total mass of this body is given, that is capital M. And what is this area? So here the material is only in between radius A and B, and the middle portion of this annulus is hollow. So we have to take the total area, that is pi b square, that is the outer radii. So pi b square minus inner radii, that is pi a square. So we get m by pi b square minus a square. And what is dr perpendicular? Dr perpendicular is nothing but r. Okay, so it is r square. So substitute all these values, that is I equal to integral dm, that is dm equal to sigma dA, and we know sigma is equal to m by pi b square minus a square into dA, that is 2 pi r dr, into r perpendicular square, that is equal to r square. So we can cancel this pi, and we can take the constant outside the integral, that is 2m by b square minus a square integral r cube dr. Here this integration is from, r is varying from a to b, from a to b. So that is equal to 2m by b square minus a square into r raised to 4 by 4, and limits are a to b. On substituting these limits, we get 2m by b square minus a square. Upper limit is b square, b raised to 4 minus a raised to 4 by 4. Okay, here this term we can rewrite in another form, that is I equal to 2m by b square minus a square into b square minus a square into b square plus a square divided by 4. So we can cancel b square minus a square and this b square minus a square. So finally we get I is equal to m by 2 b square plus a square, m by 2 into b square plus a square. Now we can check the options. So the option D is the right answer, 1 by 2 m into b square plus a square. So you got the 5 marks. It's very easy, okay? But you want to know all these small things. You have to know what is dA, you have to know what is sigma. Okay, so if you know these small things, these are the school level things, okay, concepts, sigma, dA and all. So if you know all those things, then you can easily solve this kind of problems. See another net problem. It's also a part C problem. That means 5 marks question. You look at the problem, it is very simple. You can answer within 5 seconds. That means simple problem is the problem they are asking in the C part. Wow. So how we can solve this problem? So here the problem is about angular momentum. So all of you are qualified +2. So you know what is angular momentum. That is J. J is equal to I omega. And what is I? I is moment of inertia. Right. Now what is our problem? There is 2 bodies of mass m, equal masses m. These are 2 bodies of equal masses m, and these are connected by a rigid rod, and its length is L, and it is lying in the xy plane, and if it is rotating about z axis, suppose this is z axis and this is rotating about z axis with some angular frequency omega. Okay, so we know J is equal to I omega. Then what is moment of inertia? I. We know I is equal to summation I mi Ri square. Okay, this is the first definition I told you. Okay, for a discrete system or particle system. Particles. So this is first particle and this is second particle. So I is equal to summation over I mi Ri square is equal to m1 r1 square. That is, if this is r1 radius, this is r2 radius. So m1 r1 square plus m2 r2 square. And what is this radius r? You know the total length of rigid rod is L. So small r is equal to L by 2. So that is equal to m1 is m itself. So m into r1 is L by 2 whole square plus m into L by 2 whole square. So what do you get? You get I is equal to m L square by 2. Now what we have to find out? J. J is equal to I omega. So we know Ji, that is I is equal to ml square by 2 into omega. So you got 5 marks very easily. Okay, ml square omega by 2. Option B is the answer. That is why I am telling you these are the very simple questions. Okay, so if you are preparing properly, that means if you are revising the materials every week, then you can easily qualify this kind of examination. Okay, even if you don't know anything about moment of inertia, then also you can solve this problem with the +2 level physics. Okay, how you can solve? In +2 physics, you may be now this equation. L is equal to mvr. This is the angular momentum of a particle revolving in a circle. So this is the mass m, and this is r, and this is the velocity. Then this is the angular momentum of that particle. So you can use this equation to solve this problem. Here we can, v is equal to omega r. This is the relation between angular velocity and the linear velocity. So we can replace this v by omega r. That is L is equal to m omega r square. Okay, so here there are two bodies are there, and here in this specific problem given r value is equal to L by 2. Okay, so L is equal to, two bodies are there, so L1 plus L2. That is for first body, that is m omega r. R is L by 2 whole square plus m omega L by 2 whole square. Again we got the same answer, m omega L square by 2. If you know the basic concepts, you can easily solve many of the problems. Now I am going to discuss two theorems. One is perpendicular axis theorem, and another is parallel axis theorem. So first we discuss perpendicular axis theorem. This theorem states that the moment of inertia of a plane lamina about an axis perpendicular to its plane is equal to sum of moments of inertia of the lamina about two axes at right angles to each other in its own plane and intersecting each other's at the point where the perpendicular axis passing through it. This is what J.C. Upadhyaya telling you. Did you got anything? Did you understood anything? Okay, don't worry. That is why I am here. Okay, let us consider a rigid body. Okay, let this be my rigid body, and it is in a two-dimensional space, 2D space. And this is axis, x-axis of the body, and this is y-axis of this body. And if the body is rotating about x-axis, it has a moment of inertia, we call that as Ix. And if it is rotating about y-axis, there will be a moment of inertia Iy. Then my question is that, then if you know Ix and Iy, can you find out Iz? Or what is the Iz? Simply, what is the Iz? So here you know what is the Ix and Iy, then can you find out the Iz value? Yes, that is what perpendicular axis theorem telling us. We can express this theorem mathematically as Iz, or I am calling it as more general, I equal to Ix plus Iy. This is our perpendicular axis theorem. The other one is parallel axis theorem. The definition is like this. The moment of inertia of a body about any axis is equal to the sum of moments of inertia about a parallel axis through its center of mass and product of the mass of the body and the square of the distance between two axes. Again, I know you didn't understood anything. Don't worry, I am here. Okay, see, this is my rigid body. I am considering this as my rigid body. And this is the center of mass of my rigid body, and an axis is passing through the center of mass. So if the body is rotating about this center of mass, I call it moment of inertia as ICM. Okay, now I'm shifting this axis to a certain distance d. So now this body is rotating about an axis passing through this point at a distance d from center of mass, and my body is rotating. Okay, so then what will be the moment of inertia at d? So that is what parallel axis theorem tells us. That is ID equal to ICM plus md square, where capital M is the total mass of this rigid body. Then ID will be equal to ICM plus md square. Now I am discussing some important examples. Let us consider a ring, because you know all the things about ring, because we are discussed everything about the ring. Okay, so this is our ring of mass m and radius r. And you know, if it is rotating about its center of mass, the moment of inertia I, that is, suppose this is z axis, then Iz is equal to m r square. You already know this thing. Now, suppose I want to find out the moment of inertia of this ring about this axis. Then what we do? That is where we use this perpendicular axis theorem. That is, what is perpendicular axis theorem? I is equal to I x plus I y. Here you already know the Iz value. That is Iz equal to mr square, right? Equal to Ix plus Iy. Here this have a symmetry, so Ix equal to Iy. Here Ix equal to Iy. Therefore we can call it as 2Ix, or this is equal to 2Iy. So we can find out the moment of inertia about Ix, that is equal to mr square by 2. Or we can find out moment of inertia about y-axis, that is Iy equal to mr square by 2. Okay. Next we discuss an example for the next theorem, that is parallel axis theorem. Again we are taking a ring of mass m and radius r, and it is rotating about its center of mass. So this value is equal to ICM, moment of inertia is equal to ICM. Now we are shifting this axis of rotation to here. So this is radius r, this is also radius r, this is radius r, and it is rotating about this axis. Now what is the moment of inertia? So we use this equation, that is I equal to ICM plus md square, right? So I equal to ICM, the center of mass of a ring, I think you already know, that is equal to mr square plus m, here d is equal to r, radius of the ring, so mr square. So what you get, that is I is equal to 2 mr square. So if you know moment of inertia of special cases like ring, disc, cylinder, sphere, then for any problem you can use this parallel axis theorem and the perpendicular axis theorem to solve problems. But you have to remember the basic moment of inertia, that is moment of inertia of ring, moment of inertia of disk, moment of inertia of sphere, moment of inertia of hollow sphere. Okay, if you know these values, the moment of inertia about ICM, then you can use these two equations, parallel axis and perpendicular axis theorem, to solve any problem. So these values are very important. Here I am discussing one more problem for you. Now I am considering a hollow sphere. This is my hollow sphere and it is rotating about center of mass ICM. And what is the moment of inertia of a hollow sphere? I think you are remembering that it is 2 by 3 mr square, where m is the total mass of this hollow sphere and r is the radius. Okay, now I want to know the moment of inertia about this axis. So it is rotating about this axis and this axis is at a distance r from center of mass. Okay, so what is the moment of inertia? So we again using this parallel axis theorem. So I at a distance d equal to I center of mass plus md square. So we know ICM is 2 by 3 mr square plus md square, that is mr square. So what we get? It is equal to 5 by 3 mr square. Right. Now I give you a work for you. In this lecture, we discussed moment of inertia of different type of bodies, and you make a column and write down moment of inertia of all here. So moment of inertia of ring, sphere, and etc. etc. It will really help you to recall these formulas and values. Maybe you are thinking these problems are very simple, right? Don't worry, I am going to make these problems more and more complicated for you. Now I am considering combination of rigid bodies. First example. Consider two rings. Instead of one, I am taking two rings. Okay, here these two rings are rotating about a common axis, that is this one. And both of them have same radius. So this is r and this also r. And I call this as first ring and this as second ring. Now, what is the moment of inertia of this total system? That is my question. Okay, what is total moment of inertia? That is equal to moment of inertia of first body plus moment of inertia of second body. Right, what is moment of inertia of first body? There is a ring rotating at its edge. Okay, so that value is, are you remembering that value? It is equal to 3 by 2 mr square. And I2 is also 3 by 2 mr square. So what you get, it is equal to 3 mr square. Another problem is a problem of disks. I am taking a combination of disks. Okay, these are my two disks. Now attaching another disk with this one and attaching another disk also. Okay, and it is rotating about this axis. The system is rotating about this axis. All the rings has a radius r. This also r, and all have same mass capital M. Now what is the moment of inertia of the system when rotating about this axis? So you know I is equal to moment of inertia of, suppose this is first body, second body, third body and fourth body. So total moment of inertia is equal to I1 plus I2 plus I3 plus I4. I4, right? What is I1? I1 is moment of inertia of this disk. What is its value? It is mr square by 4. Are you remembering this value? Okay. Plus I2 is also same value, that is mr square by 2. Plus what is I3? I3 is rotating about its one edge, that is equal to 5 by 4 mr square. This also we solved earlier, 5 by 4 mr square. So what we get after adding, we get 3 mr square. Again I am going to complicate the problems. Okay, now moment of inertia of reduced. Suppose this is a disk and I am removing a small portion from this disk. Okay, so from this disk I removed a small portion, this portion. Now this body is rotating about this axis. Now what is the moment of inertia? So here this is removed part, so only available part is this one. So you have to find out moment of inertia of this part. Okay, how we can calculate? Here the total mass is capital M and the radius of this disk is capital R. So what is the I? I will be equal to I total minus I reduced. Here I am considering as a disk, right? Now what is I total? Total is equal to mr square by 2 minus what is I reduced. So we have to find out the value for I reduced. Now we are going to calculate I reduced. So here this is a disk. We remove disk. So if it is rotating about this axis, we know its value. Okay, but it is shifted to this distance, that is this is the d, that is equal to r by 2. Now we can use this parallel axis theorem, that is I equal to I center of mass plus m d square. Here this m is reduced mass and capital M is for the entire body and small m for the reduced mass. So what we get, that is m r square. Here r is r by 2. R by 2 all square by 2 plus m d. D is r by 2. R by 2 all square. So what we get, this equal to mr square by 8 plus mr square by 4. So what we get, total is equal to 3 mr square by 8. Now we can substitute this value here. So what we get? I is equal to mr square by 2 minus 3 mr square by 8. Here you can minus this value from this one. Why? It is capital M and here it is small m. So we have to find out small m in terms of capital M. How we can solve? We know the surface density of entire body is constant. That is sigma for the before reducing this mass is mr square by is m by pi capital R square, right? And what is the moment and what is this density of reduced mass? That is small m by pi r. Here r is r by 2 whole square. Okay, so we can cancel this pi and r square. So what we get is m equal to 4 small m. So we got small m equal to capital M by 4. So we can substitute this value here. So on substitution we get I is equal to mr square by 2 minus 3 small m is capital M by 4 r square by 8. So what is the answer? It is equal to 13 mr square by 32. Now I am giving a work for you. Don't worry, this is a very simple problem you can easily solve. Okay, similar to this one. This is a bigger disk and I am reducing two masses. Two masses, this one and this one. From a bigger disk, I am reducing two small disks. The radius of bigger disk is capital R and total mass is capital M. And now it is rotating about this axis. Okay. Now go on the solve. Find out I. And the last example problem. I know it is a very long lecture and you are also tired. So with this problem I am stopping for today. But expect me tomorrow with lots of work for you and lots of problems. Okay, now my problem is a problem of solid sphere. This is my bigger solid sphere and I am reducing a small sphere from this one. And it is rotating about this axis. So this part I removed and only this part is there. Okay, the total mass of this body is capital M, that is bigger sphere is capital M and radius of bigger sphere is capital R. Now it is rotating about this axis and what is I? So we know I is equal to I total minus moment of inertia of removed part. Okay, that is what is I total? I total, you already know moment of inertia of a solid sphere, that is 2 by 5 mr square. Now what is the moment of inertia of removed sphere? That is equal to, here we know the moment of inertia of a sphere about its center of mass. But here in this problem we have to calculate the moment of inertia at this point. Okay, this r by 2. So what will be the I removed? We want to use the parallax theorem, that is I center of mass plus md square. We are using small m because this is small m and mass of bigger sphere is capital M. That is equal to 2 by 5 m r is here, r by 2 whole square plus m d is r by 2 whole square. R by 2 whole square. So what is its value? This is equal to 2 by 5 m r square by 4 plus m r square by 4. So what we get? It is equal to 2 m r square by 40 plus m r square by 4. I think you know basic mathematical manipulations. So what we get is 14 by 40 mr square. Okay, this is I removed. So what we got? I is equal to I of total, that is 2 by 5 mr square minus 14 by 40 mr square. Again, this is small m and this is capital M. So we have to find out small m in terms of capital M. Here what we know is mass density rho is constant. So this is equal to m by 4 by 3 pi r cube. Is for the bigger sphere, and it will be equal to rho of small sphere, that is small m by 4 by 3 pi r of small sphere is r by 2 whole cube. So what we get? We can cancel this 4 by 3 pi and we get m equal to 8m. So we got small m equal to capital M by 8. Now we can substitute this small m value, that is I equal to 2 by 5 mr square minus 14 by 40, that is 7 by 20. Small m is capital M by 8 into r square. To solve this problem, I am multiplying the first term with 4 on the numerator and the denominator. So what I get is 8 mr square by 20 minus 7 by 20 m by 8 r square. Here mr square by 20 is a common term, right? Mr square by 20 is a common term. So what we get? It is equal to mr square by 20 into 8 minus 7 by 8. So we get the final answer as 57 by 160 mr square. Okay, so today's class is over. I am also a little bit tired. I think you also may be a little bit tired, but don't forget to do all the problems that I given to you.